his address dedicating the Shippingport Atomic Power Station on May 26, 1958, the President of the United States said,
"This plant has a secure place in American history. It is the first of the world's large-scale nuclear power stations exclusively devoted to peaceful purposes. It is with pride in what has been accomplished at Shippingport, Pennsylvania, and with equal confidence in the future, that I now dedicate this Shippingport Atomic Power Station to the cause of scientific progress, to the cause of..."
This transmission line is feeding 60,000 kilowatts of power into the system of the Duquesne Light Company, serving Pittsburgh, the Steel City of the United States. The origin of this power is this atomic power station on the Ohio River at Shippingport, Pennsylvania. Primary objective: to gain information and to advance reactor technology. In addition, the objective was to obtain a nuclear power plant that would be readily operable in a conventional electric utility network and with a high availability at all times. It is the first full-scale nuclear power plant for generation of electricity in the United States. Westinghouse Electric Corporation developed and designed the atomic reactor under the direction of and in technical cooperation with the Naval Reactors Branch of the United States Atomic Energy Commission. Duquesne Light Company provided the turbine generator and is operating the entire plant. Hundreds of other companies, large and small, made valuable contributions to the project. The plant's generator was synchronized with the utility system just 16 days after the reactor went critical for the first time, and 5 days later, 60,000 kilowatts, the reactor design rating, went into the transmission lines. Now, what made this achievement possible? This film report will show, in part, what had to be done from proposal of the project to production of the power. Basically, the pressurized water reactor station operates on a simple principle, embodying a primary and a secondary heat transfer system. In the primary system, ordinary water of high purity, kept under pressure to prevent boiling, is pumped through the reactor. This contains uranium fuel and control rods. The water serves as a neutron moderator as well as a heat transfer medium. Heated by the fuel, the water flows through a heat exchanger. There it gives up some of its heat, is then recirculated by the pump, repeating the cycle. In the secondary system, which comprises a separate water circulation system, saturated steam is generated in the heat exchanger, flows through a steam drum containing steam separators, and through a turbine which drives the generator, then goes through a condenser, and as water is pumped back to complete and repeat the cycle. The use of separate systems prevents the possibility of transferring radioactivity from the primary system to the turbine and condenser. Specifications were drawn up by the Atomic Energy Commission in 1953 and included generation of at least 60,000 kW net electrical output from saturated steam at 600 pounds per square inch, ordinary water as the coolant and moderator at 2,000 pounds per square inch pressure, and fuel element life as long as possible between chemical reprocessings, with an initial goal in excess of 3,000 megawatt days per ton. There were several other stipulations, with safety within the plant and its vicinity to be an overriding feature. Here then was the basis on which the plant was to be built. A plant that would provide experience and experimentation for the benefit of future nuclear power stations, a facility in which a variety of reactor cores may eventually be operated, a plant made possible by a close working relationship between government and industry. These basic ideas evolved into this schematic plan of the shipping port station. It makes use of 4 similar loops, all supplying steam to the one turbine. Any loop can be shut down for maintenance or for instrumentation to permit studies and experiments while the plant is operating at full capacity. Behind the successful completion of Shippingport was the blazing of trails into new territory. The solution of countless problems in physics, chemistry, engineering, manufacturing, and construction. These problems, many completely without precedent, fell into 4 general areas, the first and foremost being the reactor. It posed many new, complex, and interrelated problems in design and in technology. They involved determining the most suitable fuel materials, designing the sizes and configurations of fuel elements, processing of fuel materials and manufacturing elements, determination of control rod material and design, detection and location of any failed fuel elements, the complex instrumentation needed for the gathering of highly useful information on core and plant operation, and the design of the reactor vessel. In the second area were problems involving the water. What operating temperatures in the primary system? How to control a 2,000-pound pressure? How to minimize corrosion? What measure for water purity? The third area concerned problems of assuring complete safety for persons in the plant and in the surrounding area. These problems involved shielding and measures for containment of fission products. The first barrier confining the fuel, a second one confining the primary water, and a third barrier, the plant container, surrounding the entire nuclear portion of the plant. In the fourth area were the problems of special equipment. Zero leakage pumps of unprecedented size, large remotely controlled hermetically sealed valves, instruments to continuously monitor reactivity from source to above full power levels, and operational radiation monitoring equipment. The solutions to some of the shipping port problems are evident in the physical form taken by the plant, as seen in this scale model, 1/40th the size of the actual plant. The thick walls of ordinary reinforced concrete provide effective neutron and gamma shielding. Their thickness averages 5 feet. At the heart of the plant is the reactor, inside a 38-foot sphere, topped by a dome 18 feet in diameter. The pressure vessel is over 10 feet in diameter and 33 feet high. Within it, of course, is the fuel and the control rods. 3 underground chambers, steel shells 50 feet in diameter and 1 1/4 inches thick, along with the sphere containing the reactor, make up the plant container. This is one of the 2 similar boiler chambers. A concrete shield separates the 2 loops within it, permitting access to an inactive loop while the plant is operating. The steam generator consists of this steam separator and heat exchanger. The 4 loops are capable of producing a total of over 1 million pounds of steam per hour. This chamber, 150 feet long, is used for auxiliary equipment such as the primary water pressurizer and the pressure relief system. This is the canal area for underwater handling of irradiated fuel, with facilities for core disassembly and temporary storage of used fuel. Before the plant could become a reality, most of the problems of materials, sizes, shapes, and workable arrangements had to be solved. The biggest and most important problems, naturally, were those concerning the reactor. These were solved at the United States Atomic Energy Commission's Bettis plant. There were many problems in physics to be solved. The first of these was to establish a core pattern. This required reactor physics analysis and thermal and hydraulic calculations. Mechanical design studies and investigations of fuel element configurations and materials were also being made. One of the aspects considered was the desirability of using 2 types of uranium instead of the single type of slightly enriched uranium that was originally contemplated. If some highly enriched uranium could be used along with the much larger quantity of unenriched or natural uranium, there might be many advantages, economic as well as physical. In this new concept, the enriched material was referred to as seed, and surrounding it would be a blanket activated by the seed. The pattern evolved was that of a hollow square of 32 seed assemblies with blanket assemblies both inside and out. But such a blanket would have to satisfy certain requirements. The material must pass severe tests of corrosion resistance to high temperature water. Radiation stability was necessary so that cladding would not tend to rupture. If elements failed, the failure should not progress to other elements, and the blanket fuel must contain maximum uranium loading or content. The problem was that no such fuel materials were known. It was necessary to establish an extensive metallurgical program to do research and develop technologies. It was recognized, first of all, that metallic uranium could not serve as blanket material. It had very poor corrosion resistance, for one thing. Perhaps, however, a uranium alloy could be used. Molybdenum, niobium, and silicon were among the possibilities that were investigated at Bettis. Another material being studied was uranium dioxide, UO2. Though little known, it merited study. It was corrosion resistant because, as an oxide, it was in effect already corroded. Furthermore, tests indicated good irradiation stability, and it met the other criteria. But its physical properties were not known. Even such fundamental properties as melting points and thermal conductivity had to be determined. Many aspects of the chemical behavior of the oxide were studied. These included such things as its reaction with hot water,